All right, welcome back to the online causal inference seminar. Today we're excited to have Niels Richard Hansen from the University of Copenhagen, who will talk about cyclic graphical models and causal learning. We're looking forward to the talk. After that, we're going to have a live Q&A between Patrick Forré from the University of Amsterdam and Niels. So we're also looking forward to that. Questions will be handled today by Ing. So let me quickly switch over to her.
Thank you, Dominic. So as usual, we use the Q&A section for collecting questions. That's a button at the bottom of the Zoom window. Please do submit your questions to the Q&A instead of the chat for us to better track them. And please submit them as soon as you have them and don't wait for the pause to collect the questions. Yeah, without further ado, Niels, please feel free to take over.
Yeah. Good. So you can all see my screen now and mouse point and everything. So first of all, thank you a lot for inviting me. I'm very pleased to give this talk here. And I thought I would talk about some general things about cyclic graphical models, cyclic causal models. So first I will give an introduction to this whole area and then dive more into some research that I've done myself, also related to causal learning for cyclic causal models. Let me start by using this motivating example that is research that I wasn't involved in myself some years ago, but I was very intrigued by some of the questions, and I think it's a great study. So this is a designed experiment with molecular networks where we have measurements from a lot of different protein concentrations or protein abundances under various experimental conditions. And these abundances are measured at different time points. So we have time course data. And this experiment was done as part of competition. And then participants, they were supposed to infer the causal structure and what happened when you did interventions in this experiment. And in this paper, there is this nice illustration using causal diagrams to try to explain some of the fundamental aspects of causality, like if you do an intervention on some node, and in this case, this is a protein abundance. So if you, for instance, you knock down a protein abundance, how should downstream proteins that are depending on this, how should they react? So if there's a causal edge, then you should see an effect of this intervention. But if there is no causal edge, you shouldn't see an effect. And there's also explanations about what indirect effect means and what confounding means. And these graphs, they are quite intuitive. And I think most people would just like kind of understand what they mean without even trying to formalize the mathematics behind them. But we could, of course, also use like standard directed acyclic graph frameworks like causal graphical models or structural causal models to make it more formal what these figures actually mean. But once we see one of the data results, this is an aggregated network that came out of all the submissions from the different participants. We see that there are actually cycles here. So if we zoom in, there's a clear cycle here. So again, intuitively, it makes sense that there are certain protein concentrations that are affecting each other. This is a dynamical system. But you naturally ask, what is the mathematical model behind these cycles here? How do we actually capture this in a precise way? As another example, which is something I was involved in myself, some data analysis, if we look at neuron spikes. So neurons, they communicate with each other using these electrochemical signals. And so a neuron spikes a very short burst of a signal, and then other neurons, they react to the collection of inputs from other neurons. So a typical data set here, they will look like this. So here we have, in this case, recordings from 6 different neurons. So you put electrodes into the tissue, and you see at different time points, you see the different neurons here spike, and these are very short signals. So they are typically just recorded as a single time point, as an event happening at this time point. In this case here, there are 5 different replications of the experiments, and then for each replication, we see all the events happening for each of the different neurons over time. And when I started looking at data like this, I was reading literature where people were estimating networks, and the natural question was, what do these networks actually mean? Do they have a causal interpretation? And there are definitely cycles here in these networks. So let me turn back to some early results in this area. So we can look at a structural equation model. We write it like this. There's a function here. These are the variables x that we observe, sometimes called the endogenous variables here. And then there are some additional variables that we call exogenous. And there is an equation that relates these endogenous and exogenous variables. And this might have a causal interpretation as a structural equation model. And there might be cycles in this model here. So one could have a linear structural equation model, and that would typically be written out in this way here, where this lambda function is a function of x and e here, which is bx plus e. And I write it in this slightly peculiar notation here, because this will be the natural representation later on when we talk about dynamical systems and feedback mechanisms. But this is the representation that you are probably most used to in the linear structural equation model framework, where we have x on left-hand side, and then this here can be, so we can order the coordinates so that this here is a triangular matrix if we have a directed acyclic graph, but otherwise if we have cycles, we cannot do that. But even if we have cycles, we can still solve this equation, and we can obtain x in terms of e by just multiplying by the inverse of beta on e. So early results, if you go back to the 90s by, for instance, Burtis and Richardson and Coster, using d-separation, because you could, of course, you can look at the graphs that come out of this using d-separation and just discuss the separations, even if there are cycles. So some of the results include global macro properties for Gaussian cyclic linear structural equation models. So if you have the linearity, you could actually derive global macro properties. And you could also characterize all the macro equivalences, all the macro equivalent graphs for cyclic graphs. This was done by Richardson. So if you didn't care about macro properties at all, but just looked at the d-separation rules for cyclic graphs, we could understand the macro equivalences. But it was also relatively early well known that d-separation is not sufficient for conditional independence if you have nonlinear structural equation models. So there was a gap there, even if you had these structural equation, these cyclic structural equation models with nonlinearities here, d-separation wouldn't tell us exactly what are the macro properties resulting from solving the equation. And there has been some recent progress in this area here. So there's this, I would say, monumental paper recently coming out in the Annals, dealing with all sorts of aspects of cyclic structural equations and their graphical theory. And Patrick, who is here as a discussant, is one of the authors of this paper. One new addition is sigma separation, which is a slightly different separation concept from d-separation, which is then which can then better describe the macro properties of these cyclic structural equation models. One major challenge here when you allow for cycles is the question of unique solvability, both as the equation is in itself, but also when you start intervening into the equation. For instance, do you have unique solvability, and does unique solvability, is it preserved when you intervene, even if you have it for the original equation? So this is one of the things that this paper is dealing with in great details. Now, another question is, how do we actually justify the cyclic structural equations? Where do they come from? And one way of justifying them is as equilibrium models. So we could look at a differential equation. So this is where this lambda function comes up naturally as the derivative, the time derivative of a process, such a differential equation here is called a random differential equation, because there is in this derivative there is this vector e of random variables entering. And we can characterize the equilibrium solutions of the differential equation as solutions to this equation down here. And now we see that we have the exogenous noise variables entering here, and this is an argument for why we should get these cyclic structural equations. They could appear as equilibrium solutions from a differential equation. So again, if we look at the linear structural equation model, we have a solution X, which is B inverse times E, and this can be interpreted as the equilibrium of the linear differential equation with a random inhomogeneity. So the coordinates of this linear differential equation, they look like this here, and there are certain inhomogeneities. So if these are all 0, then it's a homogeneous linear differential equation, and these inhomogeneities here, they will then determine the equilibrium point, and we can regard these as random, and then we get a random equilibrium point depending on E. So that's one way of justifying these equilibrium models. Now, if we rewrite the differential equation a bit in terms of its intuitive interpretation, so a small increment of x here is given by the derivatives times the small increment of time, then a different way of introducing randomness into a system like this is by adding some noise. So this is typically done in this framework of stochastic differential equations, where you have a drift term in the equation, and then you have this stochastic noise term, which is going to be a martingale. This could, for instance, be Brownian motion. So in contrast to the differential equations on the previous slide, the random differential equations, the noise is now part of the evolution of the process, where in the other definition, it was part of the very specification of the drift in the differential equation. And this leads to some different theories and some different behaviors. So this martingale here should be a martingale with respect to the filtration generated by the process X. So this just means the history of all the coordinates of X up to time point T. And being a martingale means that the increments of this process here should be uncorrelated with everything. So it's kind of a weak notion of independent, over time, independent noise. This stochastic differential equation model up here can also be expressed using this conditional expectation. So the conditional expectation of a small increment, given what we have observed up to this time point here, is then given by this drift times the small time interval here. I will return to this when we talk more about the neuron models, where this is a very natural way of specifying the distribution. So in terms of this lambda process, this lambda function here, we define a graph. We can just read off the graph directly. If the lambda I function depends on the xj coordinate, we draw an edge from j to I, and we call the corresponding graph the local independence graph. So, for example, if we have this stochastic differential equation corresponding to the lambda function being a linear function with B matrix being this sparse matrix here, we can read off all the edges. We have to go in along the columns here. So 3, for instance, is pointing to 1, 2 is pointing to 1, and then we have all of these here, all of these self loops here. So this would give us a local independence graph where we have all the self loops on all the nodes. And then we have, for instance, the 3 pointing to 1 and the 2 pointing to 1, etc. So we can read off this local independence graph directly from the lambda functions in the stochastic differential equation. Let me also connect this local independence graph to standard time series framework. So if we actually represent all the observations in time series data at all time points and all coordinates, all time points and all coordinates here, we can use a standard directed acyclic graph framework by having all arrows pointing forward in time. This will not give rise to any cycles. But one tool we sometimes use also in time series analysis is that we collapse this fairly complicated graph into what is equivalent to the local independence graph I just defined, where we just have one node for each of the different coordinates of the time series, and then we have arrow, if you have an edge pointing from one coordinate to another, if there is an edge pointing from anywhere in the past up to the present of this coordinate. So we have one here, for instance, because edge is pointing from the past of the first coordinate up to the second coordinate here, and vice versa, which gives rise to this one here. We also have the self loops here because the two coordinates here, they depend on themselves. And then there is an edge pointing from x3 to x2 here because we have these edges over here. So in the time series literature, this is also sometimes known as the summary graph, the roll graph, and there are probably other terminologies for this way of summarizing the full graphical structure. It's clear that you're losing some information. So an edge pointing in this direction, for instance, just says that there is a dependence in the present of this coordinate here on the past of this coordinate, but doesn't tell you anything about like how far back in the past you need to go. So you're losing that kind of information. But on the other hand, this graph here is also much simpler to work with than if you have these graphs. So even in the time series framework, it can be a useful concept. But in the continuous time framework, we don't really have this graph here because we have stochastic variables for all time points, and we only have this graphical objects, this graphical local independence graph object to work with. If we now observe only variables at a given time point, so we do a cross-sectional observation in a time series or in the stochastic processes I was talking about before, can we then say anything about the distribution? Does it have any graphical properties? So if we do this cross-sectional observation as a single time point, is this stationary distribution graphical? And if we take the simplest case again with the linear stochastic differential equation that I looked at before, it's not so difficult to show that the covariance matrix of the stationary solution solves this equation called the Lyapunov equation. So this gives an algebraic characterization of this covariance matrix. But it turns out that even though graphical constraints on the B matrix here, it implies a number of different constraints on sigma. These constraints do not really correspond to conditional independencies in general. It's only if B is symmetric that you can actually express these constraints in terms of a graphical model. Curiously, if B is symmetric, then it's actually an undirected graphical model that is the appropriate way of characterizing the constraints. And this will link this theory of dynamical processes to the classical statistical mechanics, which is the origin of graphical models, that this would be an example of an equilibrium statistical mechanics model. So I will not talk much about this. There's a completely independent line of research in understanding the constraints implied by restrictions on B, on, for instance, the covariance matrix here, or more generally on the equilibrium distribution. The important take-home message is that if I look at these stochastic differential equations and look at the cross-sectional observation, this cross-sectional observation is not a solution to a cyclic structural equation model corresponding to the local independence graph. The cross-sectional distribution may have no conditional independencies. So let me just recap here. So we have cyclic causal models have at least two different mathematical formulations, formalizations. One is as an equilibrium structural equation, which entails conditional independencies that are encoded by, for instance, sigma separation. And the other is as these dynamical structural equations whose cross-sectional distribution may have no conditional independencies. And what I will talk about for the remainder of this presentation is this latter view here. So if there are any questions right now, I'm happy to take them.
Hi, Niels. There is a question asking, can random noise be of any type, say Levy or any other stochastic motion?
Yeah, so if you go back to so the requirement up here is that this is a martingale. So it's possible that this could be a Levy process, for instance, or it could be other martingales. Yes, that's possible. But it has to be a martingale for this specification here to make sense as a stochastic differential equation.
Thank you. Other than that, we don't have any questions.
Great. So let me move on to some dynamic model specifications, and now we turn back to the neurons and the events happening for the neurons. And I look at this as counting processes. So counting processes are counting how many events has happened for a given coordinate up to a given time point. So the X process on my previous slide is now called N because it's a counting process. The ICE process will then be modeled using an event intensity. So the event intensity is, for instance, the conditional expectation of having is specifying the conditional expectation of an increment over a small time interval, which is also in this case of counting processes the same as the conditional probability that we will see an event in a small time interval, and it's given by the intensity times the length of the time interval. So returning to this heuristic or an informal specification, but it contains the main measures here. So the conditional expectation of the infinitesimal increment here, given the history, is given by the intensity that is a function of the history, and then the length of the time interval. And this process here is going to be predictable with respect to the filtration. It just means that it is something that can be computed on the basis of what has happened in all the coordinates up to just before time point t. And again, this filtration here, it holds all the information about all the events up to time point t. So let's see how this could look for the neurons. So we look at 3 neurons here, and the red neuron here has an intensity. The other neurons also have an intensity, but I just focus on the intensity for the red neuron and how it develops as we see events for the 3 neurons here. So here we see an event for the yellow neuron, and it increases the intensity for a spike of the neuron 1. But it doesn't spike yet. Later we see an event for neuron 2 here, so a spike of neuron 2, and increases further the intensity of a spike for neuron 1. And then neuron 1 spikes, and when neuron spikes, they cannot spike immediately afterwards, so the intensity drops down, and then some time passes, we see another event for neuron 2, and we see an increase of the intensity of neuron 1. And then again, a neuron 1 spike, and then the intensity drops down. So this is how the intensity models, they work as ways of specifying the distribution of event processes like this, for instance, neurons. Specific models could look like Hawkes processes. These are very popular models. So they're based on linear filters of what has happened up to a given time point. So the intensity for the ICE coordinate could be written out as this linear filter. So we have a baseline intensity giving a baseline rate for the spiking of a neuron. And then there is an integration term here, where we look at all the events that have happened for the J coordinates back in time. And then there's this kernel function here that typically decays over time, but is then integrating up all the events that has happened. And then I sum out over all the different neurons in my data. So this is known as the linear Hawkes process. Exponential kernels are quite popular. So these are kernels where these G functions here can be written as an exponential function. And one reason why they are popular is that there is this factorization of the kernel. So the dependence on T and S here, it decomposes into 2 factors, and it gives some computational advantages so that you can compute, for instance, likelihood functions, etc., in linear time instead of quadratic time. Now, the linear Hawkes processes, they have like one deficit is that they can really only act excitatory, because the intensity has to stay positive. So it's quite common also to wrap this linear filter into a nonlinear transformation. So this will give us a nonlinear Hawkes processes. So this is a general model class often used in practice. And if we recall back, how was the local independence graph actually defined? It was defined by looking at this lambda and looking at how it depended on the previous on the other processes in the system and their histories. And we can read off the local independence graph directly from this specification. So we have an edge from J to I if and only if the corresponding kernel is non-zero. And if we go up to the exponential kernels, we can see that this is encoded by the alpha ji matrix. So for these particular parameterized families of kernels, we can read off local independence graphs directly from the parameters. So that was how we could specify processes in terms of intensities. Another thing that is also of interest is the probabilistic independence model that these processes actually give rise to. And this is the probabilistic independence model known as local independence or conditional local independence that I will look more into. So we look at a multivariate counting process here with the coordinates of the process indexed by v, and we look at it over time here. And if we then have a subset C of the coordinates, we look at the filtration, which is this filtration of sigma algebras generated only by those processes that fall corresponding to C here up to a given time point is. This is the history of the C events up to time point C. And then we can define the I event intensity given the C event history. So we take the intensity for the I coordinate here, and we condition on what we have seen among the C coordinates only. So this is a projection operation that tells us how do we predict the infinitesimal evolution of the I process if we only see what is in the C events and not see everything in the system. And in terms of this projection operator, we can define the probabilistic concept of conditional local independence, or CLI. B is conditionally locally independent of A given C, and we write it like this. B is conditionally independent of A given C. If the intensity when we project down on A union C is equal to the intensity when we project down all the way down to C. So another way of saying this, that A here doesn't add any information to the I's intensity if you already condition on C. And this should hold for all coordinates in the B set here. Now this is going to be an asymmetric independence model that we call ICLI. So we have AB given C is in this independence model if and only if B is conditionally locally independent of A given C. And we cannot interchange A and B here, so it's not symmetric as usual conditional independence models are. So let us do a small recap here. So conditional local independence is an independence model among the coordinates of stochastic processes. For counting processes, it can be determined from these projection of intensities as I just described. It's asymmetric, and you can think about it as a continuous time version of gradient non-causality if you're familiar with that concept from time series analysis. So if there are any questions, now is a good time.
Hi, Niels. There are two questions. The first one asks, is in this counting process, how the causal graph looks like? I think it refers to the previous counting process you have talked about.
Yeah, so which slide are we at?
Maybe earlier. Yeah, maybe at this point also.
So on this slide, for instance, so the counting process, so the counting process for the red neuron here will start by being 0, and then it will go up to 1 here, and then when we see this is when it go up to 2. So the counting process is counting how many events has happened up to a given time point.
Great.
I don't know if that was the question.
Yeah, the question was asking about like how does the causal graph looks like, if there is a causal graph, I think.
Yeah, so I didn't say so much about whether there is a causal interpretation. So this is a question of whether you can intervene and whether these interventions are actually captured by these intensities. So So in this part here of the talk, I'm really only talking about this as a model and as a probabilistic model and the corresponding conditional independencies that it implies, or conditional local independencies it implies. So if this is going to be a causal model, then you also need to be able to intervene on the intensities. For instance, you can change the intensity of one coordinate given another coordinate. It's in this framework here, it often doesn't make so much sense to do these perfect interventions where you fix a coordinate to be something, but it makes more sense to say you increase the intensity of one coordinate, or you decouple one coordinate from another coordinate.
Thank you for your answer. We have another question popping up. Would it be possible to have an interacting particle process, such as symmetric or asymmetric exclusion or inclusion process, instead of the Hawkes process, which is a point process?
Yeah, I'm sure I'm not so familiar with the technical definitions of these inclusion-exclusion processes, but you could have many other point processes than just the Hawkes process. This is just one example so as long as you can specify the intensity of events happening, and I'm sure you can do that in most interacting point processes, it's possible, yeah.
Great, thank you for your answer. I think we are now done for the questions. Please feel free to continue.
Good. So let's continue. Let's see. Okay, so for the last part of the talk, I will now connect the different dots here. So we have introduced conditional local independence as a probabilistic concept for these point processes or counting processes, and I also talked about the local independence graph. And the whole purpose of this is that we want to connect these things. So we want to be able to express conditional local independence using the local independence graph and graphical tools. And for this purpose, we need a separation criterion. This is what we call mu separation, and this is kind of an analog of M separation or D separation, but in this context of these local independence graphs. So we can define it for any directed graph. And it's defined like most other separation concepts, that we say that we have mu separation if there is no mu open walk from A to B given C. So we need to define what it means for a walk to be open. Instead of going through the definitions, I would say it's just like D separation, except for one small change. And the small change is that the walk has to end with an arrowhead, cannot end with a tail. So it means that in a graph like this, we can take a walk from K and then in this direction here over W to I. And this walk here, even if we condition on W, which is a collider, which will usually open this path, it's still closed because it ends with a tail and not an arrowhead. And if we go in the other direction, so we start at I here, and then we go in this direction here, conditioning on W, we open the collider here. And now this walk here is open because it ends with a head. So this illustrates that there's a difference between a D separation, this is closed, but there's also the asymmetry here that a walk can be open in one direction, but it can be closed in another direction in this separation model. And then if we have a self loop like we have here on I here, we can extend this closed walk up here with this self loop. So if we walk from K in this direction here, and then do the self loop at the end, then if we only condition on W, which is a collider, now we will have an open walk because now we end with a head. But if we also condition on I here, then this will be closed at I, and then the walk will still be closed. And the way you should think about this is that the tails are actually pointing backwards in time, and the heads are pointing up to the present. So when we do this walk here, we are going back in time, and going back in time, we need to be able to get back into the present for this to be open. Right. And if we condition on the history of I, then we are blocking this path from back in time up to the present. Now this, as a purely graphical thing, this mu separation concept here generalizes directly to mixed graphs. Where we also allow bidirected errors, just like D separation, which is usually called M separation, or sometimes called M separation. And then we can play around with this separation model. We can look at it just as a purely graphical thing. It defines a graphical independence model that I call IG here, at AB given C here in the independence model if B is mu separated from A given C. And we say that two graphs are Markov equivalent with this mu separation model here if the corresponding independence models are the same, even if the graphs are different. An interesting observation is that if we only have directed graphs, so if we have no bidirected edges, then all these Markov equivalence classes, they are actually singletons. And this may sound a bit surprising, but it's really not when you think about it. It's just because that we are in a certain sense pointing all errors forward in time, and it means that we can always resolve the Markov equivalences into this single graph if we only have directed edges. Now, the whole purpose of this is to be able to express probabilistic conditional local independencies in terms of graphical independencies. So we are interested in this inclusion here that we often call the global Markov property, that if we have a graphical thing that B is mu separated from A given C in the graph, then we can conclude that we have a probabilistic conditional local independence. And the ideal case is that when we have faithfulness, so faithfulness is where we have equality here, so that the graph is expressing exactly the conditional local independencies in our probability model. So one of the first major results is a global Markov property result, and the first one was established by Vanessa Dedelis in 2008 for counting processes, and later we established a similar result that was more general. So there are certain conditions, and some of them are a bit technical. So let me just briefly say that in Vanessa's case, she showed the global Markov property when the process considered was a counting process, a multivariate counting process, and one regularity condition that I will get back to. And we gave a more abstract analysis later on, so we could also give some abstract conditions, and some of these conditions could then also be shown to hold if the martingale was a multivariate Brownian motion. But both in Vanessa's case and our case, the conditions here also include that the martingale should have orthogonal coordinates, so that's a weak version of independent coordinates. For the counting process case, this condition here just means that the different coordinates of the counting process, so the different events, they cannot happen at exactly the same time. That's the same as being orthogonal in the counting process case. Now we were interested in studying these conditional local independencies and graphical representations under projections. So where we have certain unobserved processes in the system. So here on the left, we have a directed graph, possibly with cycles. And then we have the standard graphical projection into a Markov equivalent directed mixed graph, where we replace this indirect path with a direct edge, and we replace this confounding here with a bidirected edge like this. So this is a standard graphical projection operation, also well known from acyclic graphs. And it can then be shown that the independence model among the observed variables ijk in the directed graph over here is the same as the independence model over here in the directed mixed graph. So the major results for these directed mixed graphs with mu separation are the following 4 results. So as I just said, we have this latent projection map. So we have that mu separation are preserved among the observed variables if we do this latent projection. And the most important result is this this complete characterization of Markov equivalent directed mixed graphs using mu separation, that all of these Markov equivalence classes, they have a common supergraph, Markov equivalent supergraph. So it means that you can always, in the equivalence class, you can always find a supergraph that is maximal in this set here, and you can use that to represent the equivalence class conveniently. Another important thing, which is not directly obvious from what I said up here, is that that this maximal graph can actually be recovered from the independence model. So just we don't need to know the original graph. We just need to query the independence model, and then we are able to discover this maximal DMG. And finally, it's also possible to characterize for each edge in this maximal supergraph. It's possible to characterize whether the edge is going to be in all of the different graphs in the equivalence class, or whether it's only in some of them. So this edge status here can be fairly easily determined once we have the DMG, the maximal DMG. And we call the resulting object the directed mixed equivalence graph. And I will show you an example here, which I hope will make it easier to understand. So this is an example of a directed mixed graph with 4 nodes. And we can ask, what is the macro equivalence class using mu separation? And it looks like this. There are 6 graphs. You can see that in some of them, we have the same edge. We have this edge, for instance, in all of them. But this edge for up here, for instance, is present here, but it's not present over here, it's present here, etc. And if you look at these 6 graphs, it doesn't take too much effort to see that this here is the maximal element. This is the supergraph. All edges present in any of the graphs are in this graph here. And the object representing the equivalence graph, the DMG, is then this object here where we dash all the edges that are present in some but not all of the elements in the equivalence class, and all of the other edges are present in all of the elements. So this object here is a natural target for learning, and we can then do a fairly naive learning algorithm. We can construct the maximal DMG from all conditional local independencies, assuming faithfulness. So this is essentially the proof in our paper, is showing that you can do this. If you list all the conditional local independencies, you can go through this list here, and then you can construct the maximal DMG. And this is, of course, not a very clever learning algorithm, but afterwards you can then test for removal to construct the equivalence class object. So we have a somewhat more intelligent, but still fairly slow Oracle algorithm. So it's an FCI type algorithm that will construct the maximal DMG, again, assuming faithfulness. But it's a bit more clever than just going through all the different conditional local independencies. But to implement this in practice, we need conditional local independence testing. All of the algorithms I've described here, they are Oracle algorithms, so they assume that we can query the independence model. And of course, we cannot do that in practice. We need from data to be able to test whether we have conditional local independence. So just for the last 5-6 minutes here, I will say a bit about how we can do conditional local independence testing. So I think I skipped a few slides here. So if we start out with the linear Hawkes process, as I introduced earlier, this is a very popular model, and people are often using this model here and then estimating these kernels here and using these kernels essentially to infer the local independence graph. But there are various reasons why this model is probably misspecified. For instance, this model class is not even closed under marginalization. So if you have a linear Hawkes process and you only look at a subset of a linear Hawkes process, then it's no longer a linear Hawkes process. But you can do these Voltaire expansions where you start with this first order term and then you add a second order term where you have kernels capturing interaction effects with 2 coordinates, and then you could imagine going up to higher order interaction terms, and then you can show that in a suitable sense this series will actually converge, so you can represent anything in terms of these higher and higher order interactions. And then we can try to test the hypothesis of conditional local independence of for I of j given C here. And remember, this is a matter of testing whether the intensity when we include J in the history is the same as the intensity if we didn't include J in the history. So that's the probabilistic hypothesis we want to test. So in the first proposal here, we have a working model where we say we have the intensity lambda c here, and then we add a term corresponding to J. And this will be the working model where we include J. And then we use a voluntary expansion of lambda c here. So hopefully you will have almost no or very little model misspecification in lambda c. And then we test whether this added kernel here for the J coordinate here, whether it's 0. So that's one way of doing this test. And we implemented this in this paper here on local independence testing for point processes, and applied it to the neuron case here. And we considered both the first and second order voluntary expansions. And with only the first order, we got a quite dense graph. Whereas if we included the second order in the voluntary expansion, we got a much sparser graph. There can be various interpretations of this, but one interpretation is that there was a lot of model misspecification that is then corrected for when we do include the second order interaction term here. And this is why we don't detect a lot of spurious edges over here. And then the actual algorithm here, this was not trying to, this was a fairly simple PC type algorithm, not trying to recover the full DMEG. And now more recently, we have worked on what we call the local covariance measure. So, so we have a target parameter here, gamma t here, which can be expressed as an integral with respect to a process, and then the counting process minus its compensator here. And we can rewrite this as the integral of the covariance between the process and then the difference of the intensities where we include J and where we don't include J. And this is why we call the local covariance measure. This functional parameter here depends on T here, and it captures all of these local covariances in an aggregated way. And we use this measure here to quantify deviations from the hypothesis we're interested in testing. So this function here will be constantly equal to 0 under the hypothesis. And yeah, if not all of these covariances are just 0, then it will deviate, and then we can detect deviations from the null. And the interesting thing about this approach is that using the first representation up here, it's possible to squeeze in a model of X conditionally on this filtration also. And then we have, when we model this guy here, this conditional expectation and this intensity, then we can do this root n rate double machine learning estimator, and we can get uniform level and power results for a test based on this estimator of the local covariance measure. So this is on archive right now, but it's pretty finished. So just as a small recap here on learning. So we have the global macro property it holds for dynamic models. So conditional local independence can be determined by the projected local independence graphs and U separation. For these the directed mixed graphs here, we have maximal directed mixed equivalence graphs that represent the macro equivalence class under the mu separation, and these are the natural graphical target for learning. And then some recent and then we have these sound and complete oracle learning algorithms under faithfulness. And then we have some recent developments on conditional local independence testing, also in a non-parametric way, where we do not rely on parametric modeling assumptions. So thanks to all my collaborators and foundations who have supported me, and you're all welcome to come and visit us at the Copenhagen Causal Lab if you come by Copenhagen, and thanks a lot for your attention.
Awesome. Thank you so much for the nice talk. I learned a lot. We have a few questions in Q&A, but I think the best thing is to defer them for now in the interest of time and go to the discussion. Yeah, Patrick, whenever you're ready.
Okay, yeah, thank you very much for the talk. Very exciting work. So my first question would be, how general can you define local conditional independence, conditional local independence. So for now, you're restricted to stochastic differential equation, Hawkes processes, counting processes.
Yeah, that's a really good question. It depends a little what you want to achieve. So if you go back, there's a paper by Comanche and Gigupetir, I think her name is, from 2009, also in JISSB, where they do define conditional local independence when you just have basically some special semi-martingales. But the big question is, can you prove a global macro property? And there are some technical challenges that I don't really see a way around unless you are in these special cases of counting processes and stochastic differential equations where you have a deterministic diffusion matrix on the martingale. So if you want a global macro property, and I think you naturally want a global macro property, then I don't know how to get beyond what we already know, which is counting processes, and then basically what is called Ito processes that have a drift term, and then they have a martingale term, which is a Brownian motion, but perhaps scaled with a deterministic function.
Mm-hmm. Yeah, thank you very much. I have very similar related questions. So this kind of summary graph or this local independence graph does not depend on time. But for a Markov property, you have like a stochastic process. And the question is, what is basically the internal structure that allows you for the Markov property to ignore time, to just check it in the graph?
Well, like, let me start in a different place. So if you actually have a continuous time process, which is a Markov process, like the solution of a stochastic differential equation, if you just take away one coordinate of that process, then the remaining coordinates, they will no longer be a Markov process. And typically, the coordinates will then depend on the infinite history of the process. So if you want a framework that is stable under marginalization, you almost for sure you end up with having to deal with infinite histories back in time. And you could say that the local independence graph is just taking that step from the very beginning and saying that everything is just depending on the entire history of all the other coordinates, if it depends on a coordinate at all, right? Mm-hmm. But you're right that you cannot see these fine details like whether it depends on just the previous observation or has a finite lag or infinite lag. You cannot see that from the local independence graph.
Mm-hmm. Then the next question is, for the intensity for this local independence or conditional local independence, you basically want that this lambda is not dependent on A condition on C, but for every time step, right? Yeah.
So there's a time homogeneity property that it's the same mechanism, so to speak, at all time points.
Okay. Then the question, sorry. So then the question would be, of course, how restrictive is this assumption for assuming that for all time steps? Is there maybe something that can work if one takes a time dependence into account somehow that works in maybe more fine-grained? Yeah,
I think it would be an interesting development if you have a possibility to change the local independence graph structure over time. But I'm not aware of any work that does that.
Okay, so now let's assume our process kind of converges to some equilibrium. How is local independence and the properties you studied related to the equilibrium state in the end?
Yeah, so that was a bit what I tried to address in the very beginning. So for the stochastic processes, like the solutions to stochastic differential equations, you the process will not like converge to an equilibrium point, but its distribution might converge to an equilibrium distribution. Oh, yeah, okay. Now I clicked too many times on the going back here. Let's see. Here we go. And that equilibrium distribution or stationary distribution, it's fairly clear that the local independence graph is implying some constraints on that distribution. But the general story is that these constraints are not conditional independence constraints. So contrary to the constraints that you get in your framework, where you have, for instance, a deterministic differential equation, and then you get a cyclic structural model, that does imply some conditional independencies, even if they're difficult to detect, it's nevertheless conditional independencies. Then it seems like that there are like no, or oftentimes there are no conditional independencies in the equilibrium distribution, even if the corresponding local independence graph is very sparse and does imply a lot of constraints. And the way we look at this is if we look at these algebraic equations, just for this very special case here, we see like algebraic constraints on the covariance matrix that do not correspond to any conditional independence constraints in the Gaussian case.
I see. Then the next question was how fine-grained is this mu separation in like with regard to the Markov property? If you're very conservative, you can always say if you everything declare dependent, then you will never have to basically conclude to any independence in your data. Is there like how do you know how fine-grained mu separation is with respect to this? Is there something like a completeness result, or do you expect something like that?
Is this related to whether we have faithfulness in general? Is that?
Yeah. So for instance.
Yeah, that's a good question. So for accounting processes, it's actually been very difficult to establish some examples where we can show faithfulness. Now we can come up with like single examples, but showing, for instance, the result like most of the parameters in this model give faithfulness. We haven't any examples of that. We believe it to be the case, but we don't have an example. In the stochastic differential equation case with linear stochastic differential equations and Brownian motion, where everything is Gaussian, I believe that Søren Vingel Mogensen, my collaborator, he has an example, but it's not published, where we show faithfulness for almost all parameter values.
Okay, thank you. And then next question would be, so you said like you can do some kind of marginalization or latent projections with your models in some cases, correct? And
yes.
Then what about conditioning in terms of like selection bias? Do you have something like a conditional, like if you look at conditional processes, which are kind of where there's some selection bias which you didn't know? Can you still say something about your processes in the conditional independencies?
Yeah. So we haven't looked into it. I think when we started, one reason was, of course, that we didn't want to make it more complicated than necessary from the beginning. But also, if we look at these processes, it might not be very relevant to look at like conditioning on the entire sample path of a process. So if we have these selection events, I would imagine that it's more like you have a single variable that you observe, for instance, at the starting point that might be selective, and that you could probably include in a fairly simple way. But if you want to have like conditioning also and selection properties also in the entire process of sample paths, it might be a bit complicated. And I'm not sure if you would get anything interesting out of that.
Okay, then one more question is, how do you deal, can you model interventions, like soft intervention or hard intervention with your framework? To get causal semantics or something like
yes. yes, I didn't go so much into it. We haven't done so much work on that ourselves. So Vanessa Didelis and Kjetil Roisland, they have a recent paper which is on arXiv, which has been on the way for many years, but which actually deals with the causal semantics and the identification of intervention effects. But the interventions would be like in other causal models that you interpret basically you interpret the stochastic differential equation as a structural equation, and then you intervene. For instance, you put in some kind of control mechanism, or you change the mechanism, and then the remaining part of the model will remain the same, right? And then you could do so that would be the way of making the model causal. Yeah.
Okay, so maybe my last question, I think the time is running out. What kind of formal rules does conditional local independence and this mu separate satisfy in terms of, let's say, separated rules?
Yeah, so that's in the UAI paper from 2018. There we have a long list of various properties. It becomes a little more complicated because now we don't have symmetry. So we have a left and a right version of everything. Yeah, and it's probably best just to read that paper to see all the separation properties, and yeah.
Okay, then these are my questions for the 10 minutes we had. Yeah.
Thank you very much.
Thank you very much. Yeah.
Thank you.
Yeah, thank you so much for the nice discussion. Yeah, I think it's we have a bunch of questions in Q&A, but I think it's best to just quickly wrap up and then see how much time Niels has left. So yeah, thank you so much, Niels, for a very interesting talk, and Patrick for a very nice discussion. Also, thank you all the attendees for coming and putting interesting questions into Q&A. Next time, we're going to have a tutorial actually by Philipp Bach and Sven Klaassen from the University of Hamburg, who will talk about double machine learning, a state-of-the-art framework for double machine learning in Python and R. We're looking forward to it. Hope you have a great week, and see you next time.